So it's lectures on least symmetries and general relativity. First, we build some background, and from the Riemannian geometry, we set our notation. We talked about Einstein field equation, and yesterday we discussed some of the actually four basic solutions, fundamental solutions. They're the first solutions, you will find them in any textbook on general relativity. So whenever you you discuss the solutions of Einstein field equation, those are the first four solutions. And then I mentioned yesterday, I draw a table on the board and to emphasize that there are three parameters: the mass, the rotation parameter, and okay, first we write charge, and the rotation parameter. And this is also called the no-hair theorem, that we can have these three parameters. And there's a theorem that curve line element is the most general solution for the Einstein field equations. So in some sense, you can say Kerr-Newman, because the curve does not have charge. The Kerr-Newman includes charge also. So these are the three parameters which are involved in the solution of the field equations. And yes, the thing I said yesterday, I want to repeat. This curved solution has a spin, a rotation, which means that it is a sphere, but now it has an axis of rotation. So, so it is axially symmetric solution now. So it is an axially symmetric solution. I will show another axial symmetric solution, but before going to that, so I explained these solutions in some detail, and just to emphasize the point that the solutions can be much more complicated. So these are three fundamental basic solutions, but the solutions which some of them represent physical objects, some of them we are not sure whether they represent some physical object or not, but there are many solutions that are very complicated solutions. Some of them are so lengthy that even I cannot write them on the board. So just to give you an idea, I've included one solution. I'll not discuss in detail, but just to give you an idea of how complicated things can be. So for example, this is a solution which has an acceleration also. So acceleration means that there's rotation and acceleration. So acceleration means that it is accelerating in some radial direction. Okay. The names are technical. Actually, in literature, it is called the Plebanski-Demiansky class of solutions. These two researchers gave a very, what should I say, a solution from where all the basic solutions can be derived or reduced. So basic solutions are the solutions that we discussed yesterday. So from this solution, actually from here, there's a table available in the literature and in some books. We can derive about, this solution reduces to about 20 basic solutions. So all the four solutions that we discussed yesterday, like Schwarzschild, Reisen-Armstrong, Kerr, and Kerr-Newman, they can be obtained from this solution very easily. Here you see the new parameter is alpha. A is an old parameter which represents the rotation. Alpha is the acceleration parameter. So as you can judge very well, if we put this acceleration equal to 0, we should be able to recover the Kerr-Newman solution that we discussed yesterday. And if we put the rotation equal to 0, acceleration equal to 0, it will reduce to Reisner-Armstrong. If we put everything, charge, rotation, acceleration, we should be able to obtain the basic Schwarzschild solution. So just to show you that things can go very complicated, I have shown you this line element, which, and of course, this has now uh, extra charge.
What is P?
Okay, this capital P.
Yes.
Yeah, so the capital P is defined in expression 50. So the line element 47 involves some expressions which are defined in 48, 49, 50, and 51. Just to write this in compact form, otherwise it will be much more complicated. And here now there are two types of charges. I mentioned yesterday we can have electric charge as well as magnetic charge. So this is something which contains electric charge and magnetic charge and so on and so forth. So if some of these things are absent in some situation, we will get a special case. Okay. So by special case, I mean the fundamental solution, basic solution that I discussed yesterday. So, okay, so this is called Klebanski-Demiansky class of exact solutions of Einstein field equations. And thank you for mentioning that we are only discussing the exact solutions, exact analytical solutions, and not going into the other subjects. Okay, so this line element again written in another form with electromagnetic potential, of course. And of course, you can see that the event horizon expression, which is again quadratic, but now it involves 4 parameters. So in 54, you can see that apart from mass, we have rotation, electric charge, and magnetic charge. Okay. And the requirement again is that in 54, this under the square root sign, if it is positive, we normally require it to be positive so that we have the case which is called the non-extremal case. Otherwise, if it corresponds to some physical situation like black holes, then these black holes are called extremal black holes, or as I discussed yesterday, naked singularities, which according to some people cannot exist in nature. Okay, so similarly, so these are all spherically symmetric solutions. And I mentioned yesterday that we will talk about another axially symmetric solution, which is not actually spherically symmetric. And because this will be, I will use this as an example later on. So I want to discuss that it is not that all these solutions are spherically symmetric. Although it has always, the people have always thought that most of the objects in this universe are spherical in shape. That's therefore spherical solutions have always had a special place in the literature. So whenever we solve something, first we try to solve it for the sphere. You know, there's a book in astronomy, the title is The Music of Spheres. So people have always thought that things in nature are mostly spherical, but it's not. There are other symmetries also available in nature, and the field equations, we should be able to solve field equations in other situations also. So I will give only one example of a solution which is cylindrically symmetric. So this is also an axially symmetric, but it's not a sphere which is rotating, but a cylinder. So this 55, in some sense, this is very similar to the Schwarzschild solution, but it involves, if you remember in the first lecture, I wrote another form of the field equation. There was a parameter which we call the cosmological constant. And we said that the solutions we discussed yesterday were with the field equation when the cosmological constant was 0. But this is a solution where this cosmological constant is non-zero. Okay. And I mentioned that for I mentioned that this cosmological constant is particularly important for those solutions which represent cosmological models, the models of the universe. So this is very important over there, but for our concern, we are not concerned with that pretty much here. Okay. So in some sense, this completes our second section, and now we will go to the symmetries. And for that, I would like to define something which forms the basis of all these symmetries, and that is the Lie derivative. For that, I would like to go to the board. Is it okay? Or the direction of camera? You can see the board. Okay. Okay. So I'll define the Lie derivative, which can be considered as actually a directional derivative on a curved space. So generalization of the directional derivative. It's a direct derivative of an object along some vector. Now that object can be a vector, a tensor, and if it's a tensor, it can be, of course, different the tensors of different ranks and different covariant and contravariant indices and so on. So we consider a vector field Ti with depending on some coordinates xk, and we change Ti. We want to change this Ti under motion of the observer in the direction of vector field xi. So this is a vector xi. So this is basically our directional derivative of Pi. So geometrically, we can say that is visible here. Okay. So for example, if there are some parametric curves on some space, and we have these vectors, and if there's a point P over here, and we take this to another point, we call this as P hat. In along these directions, which are represented by xi. So one of these will be xi multiplied by some constant epsilon. This is a family of, or I can represent instead of underlining, I can represent with this. So I take from this family one particular vector. So this is the increment in point P, which takes us from here to here, and these are the family is represented by this xi xk. So one of these is here. So the directional derivative, if I represent this by the derivative of Ti xk in the direction xi. So this is derivative of this object Ti, which depends on these coordinates k, and this is called in the direction. Actually, it's different people call it by different names. Some people say this is with respect to xi, some say it's along xi, and or in the direction of xi. So the different terminology people use. Or relative to xi, so derivative of t relative to. So different books use different terms for this thing. So it's the usual, the derivative that xk we add this increment and subtract from it the original position of point P in when this divided by this epsilon, which is a small parameter. And epsilon gives us one of these, from the family, we get one element from here. If I take this multiply this with T, or I multiply, take it over there and represent this thing. This thing can be represented by Pi, comma K. Xk. So this is another notation for the same thing. So if I write this, denote this by this expression, we can write that xk plus epsilon xi is equal to Pi xk plus epsilon, so Pi comma k xk and like. So this is just rearranging of terms. I've not done anything important here. I've just rearranged the terms, taken epsilon on the other side. Okay. So the coordinates of P are xi, and the coordinates of P hat, this is an increment in this xi. So this xi plus xi. Okay. And this is coordinate transformation from P to P hat. So this coordinate transformation, so it will involve an object like a matrix with two indices, because we are transforming this to. So for example, the coordinate transformation for the coordinate xn is represented by xn minus epsilon xi and xk for the new coordinates. And if it is an object like a matrix with two indices, so this will be in new coordinates given by this prime with this, the matrix of like Jacobian. So the matrix of the partial derivatives of the coordinates of the new coordinates with respect to the old coordinates. So this will be n comma I. So now this will be an object with two indices. So if we write the components of our this object P and transform the coordinates, the components, and write it with component form, components of Pn at point P hat, which is the new position over here. So now this is the transformed component, new coordinates Tn prime at P hat. This will involve this matrix of transformation Ni prime Ti with new position of xk plus epsilon xik at this point P hat. In this expression, I will substitute for this object, I will substitute this. And from this, so I can call this as 2, equation number 2. So substituting from 1 and 2 in this expression. Okay. So I'll say this multiplied with this expression. So this will be delta n I minus epsilon xi n comma I and multiplied by this expression, which is EIP plus epsilon EI comma K at P xi K. And now I open the brackets, take the product, and we will get. So you see that when this is multiplied by this, only the index will be substituted. So canonical delta, I think I mentioned in the first lecture, acts as the index substitution object also. Like a tensor will substitute the index. So it changes from I to n. Obviously, when I is not equal to n, this will be 0. Second term, if I multiply here, this will be epsilon T n comma K P xi K. So again, this is multiplied by this and it's substituted I for n only. That is all that it has done. And now this is multiplied by this and we get epsilon K P K P. So this is expression 3. The expression which involves the epsilon square, we have ignored that. So the quadratic. So from here we can. Okay, yes. Now we don't need this. Yeah, we can. Okay, so now what I'm doing, I'm taking this on the left hand side. And this becomes T n P hat minus T n P is equal to epsilon T n comma K. Comma, you remember, is a partial derivative with respect to K. And P xi K minus xi n comma K P K and P. I think I should make repeat this, that this vector xi and similarly other vectors, if we, there are two types, there are two, I mean, ways to represent this as a vector. Either I will draw a line which will show that it's vector, or I will put an index. So sometimes we write, and this is called the initial notation of the tensor notation of vector. And if I don't write this, then the line is the vector notation. So both the notations are used here and in books. So now we define the Lie derivative. So Lie derivative is it comes in the title of these lectures. So perhaps I should mention for those who may not. It's after the name of a famous mathematician Sophus Lie from Norway. And we will talk about Lie groups and Lie algebras also and so on. So so the Lie derivative of Tn with respect to xi. So okay, so we can write a line over here or an index at the same thing. So relative to xi or with respect to xi or in the direction of xi, so people call it by different terms, different phrases, but it is represented by this italicized L with this of the object for which we are taking the lead derivative, and here in the subscript we write that vector along which we are taking. So this, and it is the limit when epsilon goes to 0. So we are dividing this by epsilon on the left hand side is being divided by this epsilon, and this is actually the derivative of the definition of the lead derivative. And t and prime we had minus t and b over epsilon. So it's like directional derivative. Okay. And in our case, this right hand side is the expression. So if we want to calculate, so it's the definition, but we have, when like the ordinary derivative, we have a definition, but actually when we want to calculate the derivative, the techniques and the methods. So the right hand side is a simpler method for actually calculating the components of the derivative. So in that sense, we can say that the lead derivative of Tm along this direction is actually the first term involving the partial derivative of the object, the vector in case, contravariant vector in this case, xk, and the second term which involves the derivative of the vector itself, along which we are taking the derivative. So what is this? This is the lead derivative, the definition for a contravariant vector. So this is the lead derivative of a contravariant vector. And similarly, we should be able to write the definition for a covariant vector and higher order tensors and so on and so forth. So I just mentioned the difference. How can we write? So the first term always will be the partial derivative of the object that we are taking, the derivative. Okay. The second term will be the derivative of for this vector. Now, whether this will be a plus sign or a minus sign and how many terms will there be after this first term depends on the order of this object. Of course, if it's a vector only, then there will be only two terms. If it's a contravariant vector, there is a minus sign. If it's a covariant vector, there is a plus sign. And now you can guess that if it's a tensor and it's a contravariant tensor of rank 2, there will be two terms with minus sign. If it's a covariant tensor with rank 2, there will be two terms with plus sign. If it's a mixed tensor, second rank mixed tensor, then there will be one term with negative sign, one plus, and so on and so on. So it depends on the order. So I will write only two. This is for the contravariant vector and for covariant vector. The d derivative will be Tn, and this is vector xi, and this is Tn comma k, xi k plus. Now this will be plus sign. That is the only the difference. Xi k comma n, and it's a rank 2 tensor of rank 2. And this is very important for our future discussion because we will mostly be talking about Lie symmetries of tensor of rank 2. And most of them will be covariant tensors of rank 2, like metric tensor. So the least derivative of the metric tensor, for example, with respect to xi. So the first term is the partial derivative of this tensor multiplied by this. And of course, there will be a summation. I told you in the first lecture that the free indices are mu and nu only. So if we introduce a new index, that has to be a dummy index. This I mentioned in the first. So if there are any new index coming apart from mu, that must be contracted by the same index in the opposite position. This is a requirement which is called the first I mentioned. This is the Einstein summation convention or contraction of indices. We call. Okay, apart from this, we will have two terms. We know that they will be with a plus sign because it's a covariant derivative, and they will involve the derivative of this vector xi and not this tensor. So lambda nu xi lambda. So this will be common plus. So why there are two terms? You can guess easily because there are two indices, and for every index there will be a term. So this expression will be used later for actually working out the least symmetries. So giving definition is one thing, and I said that I will actually try to work out some examples of how we construct these symmetries generators and the algebras. So because we will be mainly discussing tensors of rank 2, and they will be covariant tensors of rank 2. So this expression is very, very useful and important for our future discussion. So with the Lie derivative, this concept is accompanied by the concept of Lie bracket. Which is very useful even in classical mechanics, and of course it's important in quantum mechanics, branches of physics, and so on. So the bracket is defined when we have. So if I just mentioned that we can write vector without indices also with the vector notation. Actually, when we go through some book which is mainly written for what we call as pure mathematics, you will find mostly these objects only in vector notation. And they're not mostly concerned with the components, what will happen to the components. So I am trying to keep both the notations side by side because we need both of them, not only the concept, the definition, but we will actually need to calculate the components when we solve the field equation, which have some physical significance, maybe from astrophysics or cosmology, whatever, and apply these concepts to those. For that, we need all these expressions actually written in component form. Otherwise, in just this notation, the students never know how many equations they will get and how many components, and they never know whether what they are calculating is correct or incorrect. So this thing, that d derivative of eta with respect to xi, this is sometimes represented by this object. And this definition is that we apply xi on eta, which is actually the d derivative of eta with respect to xi minus the opposite of this. And you can see that this is called commutator bracket also, which is so important in quantum mechanics and even ordinary mechanics. And if this is zero, we say that they commute. And this is a skew symmetric and anti-symmetric bracket, which means that this will be the opposite of this. So by definition, it is clear that this is a skew symmetric bracket. And so this is the negative of the Lie derivative of xi. So this is important. So let me ask you, is this clear? And if there are no problems in this, because basically this will be the concept that is starting our new topic, new section. Okay, so I think things are clear. Now, with the help of this Lie bracket, we will construct our structures on this that form the basis of the subject of this Lie symmetries, group theoretic methods. So different names, continuous groups, Lie symmetries, and I told you that most of the results I'll be talking about are given this book with by Graham Hall, and the title is Symmetries and Curvature Structure in General. Okay, the two important properties I would like to talk about: the linearity, the Leibniz property on when we apply this Lie bracket on the functions, the product of functions and the sums of functions. They're almost clear from the definition, but I should mention them. So if I apply them on alpha f plus beta g, for example, so this is beta f plus beta. So the usual linearity, the Leibniz property on the product of two functions f and g. So g f plus f and so Lie bracket XL, a binary operation between two objects. So after after this discussion, it becomes very easy for us to define Lie algebra, what we mean by Lie algebra. Just combination of these nice properties that we have already discussed. So Lie algebra actually is a vector space over a field F together with a binary operation. So I think I've already mentioned that if this Lie derivative is zero, we say these two vectors commute. With a binary operation, Lie bracket. This the bracket of two objects, it satisfies the following four properties. So the important thing to note here, as I mentioned, is this Lie bracket is actually a binary operation between two vectors in this case, but we can have other objects. So the first is bilinearity. So bilinearity means that if we have alpha xi plus beta beta with some third zeta, I think it's called zeta. So this should be equal to alpha xi beta plus beta beta where alpha and beta are from the field are scalars. They belong to the beta. So this can be a real field or a complex field. And similarly, we can write this as in the second bilinear. Sometimes they write two expressions for this. One where we have taken the sum of these two and then taken bracket with the third one. And in the second expression, they take this as a separate and add these two. So it's the same thing. Bilinearity property. Second is called alternativity. So alternativity means that xi applied on xi is 0, which is obvious from the definition. So we have xi applying on xi. Number 3 is the Jacobi identity. I think I should write it. So Jacobi identity means that we have a Lie bracket of xi and zeta, and we are taking the Lie bracket of this Lie bracket with another vector. I should write a line over here also, because they are all the same. Plus this eta combined with zeta and the bracket of xi plus this zeta with xi and this eta. This should be equal to 0. So when we have three vectors, any three vectors will satisfy this Jacobi identity. And anti-commutativity, I have already mentioned, but this is a requirement for it to be a Lie algebra. Anti-commutativity means that xi applied on eta is equal to minus of eta. So this is the four conditions when they satisfy this vector space. So remember that this is a vector space. This is called a Lie algebra. And if it's a vector space, its dimension is actually the dimension of the Lie algebra. So dimension of the Lie algebra is its dimension as a vector space, which means the number of elements in its basis. The minimum number of linearly independent vectors. And we will see those vectors will actually be the generators coming from the solving partial differential equations. Actually, this forms the basis of the subject which people call the solution of partial differential equations by group theoretic methods. So this is actually we are only applying it to general relativity and those problems, but actually the group theoretic method differential equations, the subject also starts from here. So these vectors which we will see later on, they will be generators, and the minimum number of those linearly independent vectors form the basis of this vector space, and that is actually the real algebra, the dimension of the real algebra. So if these vectors are represented by generators, as I said they come from the, I think they're clear actually. So this if these vectors are presented by, so if we have, for example, a set of vectors, x1, x2, x3, and so on. And if this forms a Lie algebra, then these vectors, I will actually show you with the help of examples that in the case of the solution of PDEs, and we will see that actually these are PDEs, you can see these are PDEs. And from these solutions, we will get the set of generators. And these generators, they form a Lie algebra, then they also satisfy another property which will be used later, that is closed with respect to this operation of the Lie bracket. So whenever we take two vectors, apply Lie bracket on them, we'll get some vector from the same set multiplied by some constant, and these constants with three indices, they are called structure constants. This notation actually is very useful because with the help of only this structure constant, you can see what are those vectors which we are using to, which we are applying the bracket on, and what is the result of this. So only this constant tells you a lot about these three vectors. So in actual example, it's sometimes very useful to use the structure constants for brevity. It makes the notation brief, and I will show you some examples how we can do this. That if we only mention the structure constants, we will get information about these three vectors. So it's closed with respect to this operation. So after this, let me come to the I will discuss some symmetries, these symmetries on these different objects. But the first and base, yes.
There is question someone is
Yeah.
asking, how the d derivative is connected with different structure like as in the case of scalar vectors, tensor.
Let me see what. Well, let is connected with different structures, like as in the case of scalars, vectors, and I just raised this is the definition. Okay, so they're there. So this is the Lie derivative of a vector, and this is the Lie derivative of a second rank tensor. So it's not clear to me what he or she, Akhtar was saying. And if you're asking about the applications and why is it useful and what are the so that is our next the subject of our discussion now that I will be doing. So the first symmetry I would like to talk about after this basic notation and definition and so on is the killing symmetry, the isometry. Okay, so killing vectors. This is the first and fundamental symmetry. And this actually is mostly comes by the name of isometry in differential geometry. So isometry, what is isometry? Iso means same and metry means the distance. So any transformation that preserves the distance between 2 points. So you have 2 points in one manifold, if you allow me to say. There are 2 points on one manifold and you take them, you transform them and take them to another manifold. So other things may change, but if the distance between those 2 points remains the same, then that transformation under which we have done this, move those points is called an isometric transformation. So isometry or isometric transformation. And what is this? This is exactly the same thing. The distance in Riemannian manifolds is represented by metric tensor. And if we take its Lie derivative along some direction xi, and if this is preserved, then xi is an isometry or a killing vector. Which we will denote by kv. And this is after the name of Wilhelm Killing, the German mathematician. And this equation, which I have not erased so far, okay, if we put this equal to 0, this equation, then this equation is called Killing equation. And its solutions, this is the equation, is a partial differential equation, and its solutions are called Killing vectors for that manifold. So this means the the Lie derivative of the metric tensor in that particular space, or we will be talking about space times as I mentioned in the first lecture. So the Lie derivative of the metric tensor, if it is preserved under this vector, then this vector is called a killing vector or an isometry of space. This is a fundamental property. Actually, this defines, I was mentioning axial symmetry yesterday. This actually defines this metric structure, the geometry of that space. That what isometries, what killing vectors are possessed by some particular space. This is a basic fundamental property. And other symmetries are in some sense general ideas and generalizations and extensions of this basic symmetry. So this is the first and foremost basic symmetry. And now you can see that, for example, if we have a space-time of four-dimensional space, and so if this is a definition of Lie derivative, but if we put this equal to 0, now this becomes a killing equation. Okay, so this is a set of homogeneous equations, and of course these are symmetric. So in a four-dimensional space, as I mentioned, somebody asked the question also, how do we know how many equations we have? I told you that this, if it's a symmetric object with two indices, then we know that there are 10 equations. So this, in a four-dimensional space, in a space-time, for example, these are actually 10 partial differential equations. And what we are solving it for, we're solving it for this xi vector, which is the killing vector. We know the metric tensor for the space, and we construct this set of four equations. We solve it for the vector xi. We get a solution, we get the generators. We write down the generators, and we see that those generators are governed by the properties of the conditions we mentioned for a Lie algebra. So those generators form a Lie algebra. Then that set is closed under the operation of Lie bracket. So after this basic principle, and it's a very complicated and tedious set of equations to solve. You can imagine that if this is a four-dimensional space, it will have four components. And even if it's a diagonal metric tensor, we saw in yesterday's lecture that some metric tensors in general relativity can be diagonal, some may not be diagonal. I've shown you some very complicated cases also where they're not diagonal. So even if it's diagonal, there will be four components of the metric tensor and four components of this vector, and we need to extract these four components from this equation. I said it's not easy to do, but I would like to do one example at least with all the very simple example, perhaps the simplest, I'm not sure, but which is the surface of a sphere, so that we know what actually we do and how we calculate these components and actually extract killing vectors and see what are the generators and so on. So a simple example. So simple example, I think this is the simplest. You will take a Euclidean plane in polar coordinates. Euclidean plane in polar coordinates. So you know the metric tensor is given by, sorry, the line element or metric tensor the same. We can write it by dr square plus r square d theta square. So two-dimensional Euclidean plane, but I'm writing this in is this the simplest, or you can think of any example simpler than that? I think we can think of an example. That is right, the Euclidean plane, but in Cartesian coordinates. So that will be even simpler than this. Okay, so in matrix form, if we denote this metric tensor in the form of a matrix, this becomes 1, 0, and 0 r square. Okay, and this, I am putting this equal to 0. And now this is killing equation. And I denote it by star because I will be using it. So we have two coordinates. X1 is r and x2 is theta. Only two coordinates, 1 and 2, x1 and 2. And this is metric. So two coordinates, two-dimensional space, so we will have three equations. One equation will be for 1, 1, then for 1, 2, and 2, 2. So sometimes we call them as a K11 equation, K12 equation, K22 equation. So if we want to use that notation. So for 1, 1, when we take mu equal to 1 and mu equal to 1, the first equation is G11. I will do this example in detail so that those who have not seen it, these things, they can follow it. I told you for complicated cases in high dimensions, it's not possible to do this in maybe one whole day. I cannot complete this. It's long, lengthy calculation. Okay, 1, 1, comma lambda, xi lambda plus g lambda, mu is 1, xi lambda plus g 1 lambda xi lambda comma mu, sorry, comma 1. This is 0. Done correctly, or I hope it's okay. I've not done.
In the second, I think zeta lambda 1.
Yeah, it's comma 1. Yes. Now it's okay. Okay, so here you see that this G11 is this, and its derivative is 0. And the derivative with respect to r or theta. So the first term is 0. And here lambda can only be 1. It cannot be equal to 2. Okay, so there's some wants to ask, may, I think I complete this example and then take up this example. Okay. This is not, you cannot see the board, huh?
Yes.
Okay. So I should maximize.
We have not seen it.
Okay.
Check first. I should complete it.
Okay, so we can only put this 1 here. We cannot put 2 because this diagonal matrix is this example. And xi 1, comma 1 plus here also this only d11 xi 1, comma 1 equal to 0. And this means we have this equation 1 xi 1, comma 1 equal to 0. This is our first equation. The second equation is a 1-2 equation. Okay. So if I write 1-2 here, this is 0. The first term is 0. Second is 1, 2, xi, sorry, it's lambda. Lambda mu is 1 plus it is 1 lambda xi lambda comma 2 equal to 0. Is it? Okay. And actually G11 is 1. So this becomes xi1 comma 1 equal to 0. So here lambda can only be 2, it cannot be equal to 1. So it's 2, G22 xi2 comma 1 plus G11 xi1 comma 2 equal to 0. And 2 is r square. R square xi2 comma 1 and 1 is 1. So xi1 comma 2 equal to 0. So this is our second equation. And the third equation, we take 2, G22 comma lambda xi lambda plus G lambda 2 xi lambda comma 2 plus G 2 lambda xi lambda comma 2 equal to 0. These two are the same. So this becomes G2 to this can be 2 only because G2 to depends on R square. So it depends only on R, not it's 1 only. It depends on R only, not theta. And these two are the same. So we can write 2 times G2 to xi 2 comma 2 equal to 0. Okay. So the derivative of 2r square is 2r. 2r xi 1 plus 2 r square xi 2 comma 2 equal to 0, or when we simplify it, this becomes xi 1 plus r xi 2 comma 2 equal to 0. So let me write these three equations. Xi 1 comma 1 equal to 1. This is equation number 1. Xi 1 comma 2 plus r square xi 2 comma 1 equal to 0. This is equation number 2. And xi 1 plus r xi 2 comma 2 equal to 0. This is equation number 3. So this is our set of PDEs that these are three components of the vector xi. We solve these and obtain these three components. These are the three components of the isometry on this space, on this Euclidean space in polar coordinates. So from the first equation, this is easy to see that this means there's a function of theta only. Xi1 is a function of theta only, it does not depend on r. There is some function of theta because we have only two r and theta. So this is a function of theta only. If we put substitute this in equation 2, equation 2 gives us xi1 comma 2. Comma 2 means derivative with respect to theta. And it's a function of theta only, plus r square xi2 comma 1 equal to 0. Okay. And xi2 comma 1 is equal to, if I take this on the other side, this is minus xi1 theta comma theta divided by r square. So I integrate it with respect to r. So integrating it with respect to r gives us xi1 comma theta, function of theta over r plus a function depending on theta, because I integrated with respect to r, so therefore there will be a function, an arbitrary function depending on theta. So now this is the form of xi1, this is the form of xi2. We have used first and two equations. I substitute both of them in equation 3. So now 3 becomes, this is xi1 theta plus, this will be multiplied by r. So therefore, this will be, and this will be derivative with respect to theta. Again. xi1 comma theta theta, a function of theta, plus r times g, a function of theta, equal to 0. Now, if we compare the coefficients of r, this term will be separately equal to 0 and this will be separately equal to 0. So this means g comma theta as a function of theta is equal to 0, which means it's not, it does not depend on theta, and it is a constant c. It is a constant c. And the other part of this equation is xi1 comma theta theta plus xi1, and this is a function of theta, this is a function of theta equal to 0. And we know that its solution is c1 cos theta plus c2 sin theta. And this we can call as c3 now. And now this is the expression for xi1. xi2 can be written from here. So xi2 is 1 over r, and its derivative with respect to theta, minus c1 sin theta plus c2 cos theta plus c3. So if we want to write this killing vector in this, we can give it this notation. The first component is c1 cos theta plus c2 sin theta, and the second component is 1 over r minus 1 over r c1 sin theta plus 1 over r c2 cos theta plus c3. I can erase this one. So the generator for this very simple example. So these are three parameters with three constants involved, is C1, C2, and C3. So we can write the three generators corresponding to these three constants. So x1 will be written from C1, for example. Okay. So this is cos theta and d by the r minus 1 over r sin theta, and this is d by d. So this is an operator. Okay. So with the first component, we'll have the d by dr, and from the second, the expression of the second component, they will be for d by d theta. Because r and theta are the only two coordinates. So this is the first generator. The second generator will be written from C2. So this will be sin theta d by dr plus 1 over r cos theta d by d theta. So these are actually vectors, okay? Generating vectors or generators. They are called generators also. X3 is only in the second term, so this will be d by d theta. So this is how we construct generators from here. And when we, okay, there was a question also, what the closure property is closed. So you can see that you apply any of these two. Take x scale, xl, any of these two, you will get one of these two. Okay. So Cj, Kl, Xj. So these are operators. You can apply this on this and this on this, and then you will see all the properties of Lie algebra. This question somebody has also. So all the properties will be satisfied here. Commutativity, anti-commutativity, alternativity, recombinability. So this is actually, I leave this as an exercise for the student to check whether it is closed, this algebra is really closed or not. So you see, this was very simple example in two-dimensional coordinates that we have done. Of course, we cannot do the all the other examples in detail, four-dimensional examples and the other symmetries of the other tensor. This is the symmetry of the metric tensor, the first symmetry that we have defined, and we obtained these three generators. And I think we should, before next, we would like to go to the, actually we would like to talk about killing vectors in higher dimensional spaces, and then the symmetries of the other tensors. For example, the Ricci tensor we have studied, the matrix tensor, the Riemann tensor, and so on and so forth. So, and what is the relationship of these killing vectors with all those other symmetries? So we will discuss in the next lecture. Okay, so I stop here and see if there are any questions. If you have any questions, and I will talk. In the chat box, we see that, yes, somebody wants to ask the question on the microphone.
Should I unmute it, or you want to answer the other question?
Okay, so in discrete symmetries is a different situation. These are continuous symmetries. So no, it will not form a Lie algebra. We have seen this in a very simple example, and in other examples in the next lecture we see that we have always, these are continuous symmetries, and we always have a closed Lie algebra in our cases. The Lie algebra is always closed, and actually this this is a test of our calculations also. If we are not able to close the Lie algebra, this means we have done some mistake. So you will see that in these in the case of continuous symmetries, it's always closed. And there are the symmetries you're talking about, discrete symmetries, and then there are some approximate symmetries and so on. There the situation is different. They may not obey this property. And yes, somebody wants to ask a question on microphone. Yes, please go on.
Okay, thank you for the opportunity. I want to ask you, what is the equation of motion of the neutrino particle in the Kerr-Newman black holes, and what is the symmetry group can be used? I repeat again, what is the equation of motion of neutrino particles in the Kerr-Newman black holes, and what is symmetry group can be used? Thank you very much.
Okay. Okay, so you're talking about the neutrino particles. There was a question yesterday about the equation of motion of other particles, for example, the massive particles. And I said yesterday also that we are dealing with the classical general relativity, which does not need the concepts from quantum mechanics. I said that there are other branches where we need concepts of from quantum mechanics combined with classical general relativity, and there are different approaches for that. For the classical particles, as I mentioned yesterday, and I mentioned the books also, for example, the Chandrasekhar's book and other books, there the equation of motion is given from the geodesic equations. They're charged particles, the massive particles, and photons, the path of photons around Kerr particle, and so on. That can be studied in classical general relativity. But for the other objects where we need quantum mechanics, I'm not actually, I'm confining myself only to the classical results, not the quantum gravity and things like that, because that will be another subject. And somebody asked about the why we would like to go beyond general relativity, and I said in these lectures I am also confining myself to the four-dimensional Lorentzian manifolds only. Okay, then there's a question, what is the importance of killing vectors and how they are used, and mention the book where there's to the Lie algebra portion. Okay, I mentioned some of the books, and okay, some concepts are given. Let me see. In this book by Graham Hall, yes, it's chapter 5 deals with Lie groups, Lie algebra, and Lie subalgebras. Okay. I'm not sure if they've done examples in this detail that I've done here, but the basic theory and theorems they are given over there.
Maybe you can write the name of the book.
But I mentioned this on the first lecture. Yeah. I mentioned the name of the books where we deal with this subject and which I have used for preparing these lectures. Okay, so what's the significance of killing vectors? So these are directions along which the distance is conserved. And these are important because the transformations which can change other things, the relationship between the 2 points, the other properties and the relationship between 2 points. But if the distance is not changed, then those transformations are actually some solutions have been calculated in general relativity by using this property. So they first find out the killing vectors and then see what spaces do this are satisfied by these killing vectors, and then come up with new solutions. So this is one of the method by which we can generate solutions and find new solutions of the killing of the Einstein field equation, not only by using this killing vectors but other symmetries. And then in the next lecture, I will show you how we can find the new solutions of Einstein field equations by these symmetries. So this is the application here in Lorentzian manifolds, where we are dealing with general relativity. Otherwise, this concept of isometry is very old in differential geometry. This is a basic concept where we talk about distance preserving maps, the isometries. Okay. Is there some computer programs for following this system? Like they solved the 3 by hand? Yes. So the people who do group theoretic methods in differential equations and PDEs, yes, they have developed packages, and they use those packages and those programs to find out the symmetries and generators. So the answer is yes, but whether we can use them for all sets of PDs and ODs, and it's not clear to me. And I've talked to some people who are working in those areas. They say that those programs actually do not solve all sets of these equations. Now, which systems do they solve and which they don't, I am not clear. I don't know, but there are, and then there are other types of symmetries. I mentioned the approximate symmetries and the other generalization of these symmetries. So the computer packages are not available for all of them. So yes, I know there are some packages, and people do use them to find out these symmetries, but it's not true generally. Yes, it's okay now, I think. Okay, so we leave it there. And so far, thank you very much.